In this video, we are going to write a function that does prime factorization of an integer. There is a theorem that's called fundamental theorem of arithmetic, which says that all numbers, all natural numbers, can be produced as the product of prime numbers. Even the non-prime, even the non-primes, all the non-primes can be factorized as the product of primes. So this means that numbers like prime numbers like 5 are of course the product of numbers like 5, and 6 can be expressed as a product of 2 times 2 times 3, a product of prime numbers. And of course another number such as 28, that is 2 times 2 times 7. Oh, I should be more careful with this. 2 times 2 times 7, that's 28. And 15 equals to 3 times 5, etc. All numbers have prime factors, and that's what we are going to code in this video. So public static, what this is going to return, what this function is going to return, is an array list of integers which are the prime factors. So factorization, let's call it prime factorization of what? Of an integer. I really think it's going to be quite straightforward to do it. We're going to have a result as an array list, and and since we're looking for prime numbers, let's try to look at all the prime numbers up to and including the number we are looking for. Isn't that right? So if we're looking for number 5, for example, we would like to compare it not necessarily to all the numbers, but since we're doing prime factorization, we need to look at all the prime numbers up to and including n. So let us begin. First of all, we will write a for loop. Check all the primes size I++. And what is this? I hate the autocomplete. So first thing we're gonna do is to check whether n can be divided by the prime number we're looking at this iteration. So if this, we'll check the modulo. If this equals 0, then the result add primes get I. So this number is a factor of this number is a prime factor of n. Where's n? Here it is. So I is a factor of n, and also I should also add all the prime factors of n divided by I. Not I. Primes.get I. So if we have n equals 6 and I equals 2, I would like to add to the result the 2, but also all the prime factors of 6 divided by 2, which is 3. Am I right? Yes. So if we have 12, 12 is a better example. 12 divided by 2 is 6. So 2 is a prime number and the prime factor of 12, and I also want all the prime factors of 6, which is 2 and one more time, and 3, which means I want the resulting array to have the following numbers: 2, 2, 3. All right. So result dot add. Can I add a collection? I think I can add a collection. I could add prime factorization of n divided by primes dot get I. Yes. So first thing I'm gonna do, I would like to make this a little bit more readable. Prime, the current prime number, is primes get I, so I only have to write prime here. So we add the prime factor. Let's call it factor, but it's not determined that it's a factor, not until we get into the if statement. So we add the prime to the factors, so I'll call it factors to be more understandable. So I add all the prime factors here. I think this is not the correct way to write this. And you know why? Because in the first iteration, it will add all the prime factors, 2, 2, and 3. And then in the next iteration, it's going to look into 3 and add again these prime factors. Therefore, I think the proper way would be to return after adding all the factors. I should do this. So find the first factor, find the first factor, the prime factor, and add all the prime factors of what's dividing it. Primes here. That's a bit more understandable. I hope, hopefully at least. Anyway, let's try and do it. So do the prime factors of 24 or 12 in our case. I have errors in my code. Prime factors. Let's call it prime factors. Yeah, I think it's a better name. Prime factors. It's a recursive function, so hopefully I don't blow my stack. So 2, 2, 3. Awesome. How about 24 or 36? 36. It's 2, 2, 3, 3. 25. It's 5 and 5. What else? What else? What else? 100. That's a pretty nice implementation. I did not expect it to work so neatly. Well, you see, the for loop in here is not optimal. It doesn't do a specific amount of loops. So I would rather switch it for a while loop. So while something something, the initial value is int I equals 0, and at the end of the while loop I++, and I will put in here all the code. So while well, you're definitely gonna find at some point, let me put this a different way, you're never gonna surpass the size of the primes array, because if n is a prime, then the last element of the primes array is going to be the n itself, which means that it's gonna exit the loop. I mean, the exit condition should be n prime different than 0. So while n primes dot get I, since I can't do it any sooner, as long as this is different than 0, all you have to do is I++, and when you're out of it, yes, so search for the first element of the primes array that divides perfectly n. All you have to do is do a ++ of I, not do anything else. When you find it, exit the while loop and do the stuff over here. And these two occurrences of prime, well, I won't get away with using, I don't think it's a good idea, but anyway. So if n is a prime, then it will just iterate through all the primes array and until it reaches n, at which point it will add the prime and, well, what happens if we, let's see, if n is not a prime, then it's gonna return the elements. Wow, how nasty. And I'm already 13 minutes in. Well, let's wrap this up for now and do another video to debug this part. Thanks for keeping up with me for so long, and I'll see you next time, which it's gonna be a rather short video to solve the problem.